Okay, folks, so this is that second video that I've been promising. Here we go. This will continue chapter 8 and move us along closer to the test, which will be coming up before you know it. Okay, so let's start by looking at acid-base neutralization reactions. So this is another driving force. All acid bases, if we break this down, H plus and OH minus will neutralize to form water and a salt. Typically, that salt, if it's ionic, will cancel out, and we're left with the net ionic equation being H plus and OH minus forms water. Now, why doesn't this simply go backwards? It's because water is a liquid. It is a pure liquid rather than aqueous. And so, because it's switched states of matter, we no longer break this apart into H plus and OH minus. So, now this is true for every strong acid. Every strong acid does this. However, weak acids and weak bases will not do this properly. And so, if you run into this on the homework, the weak acid does not, even though it's aqueous, does not break apart into its ions. Strong acids, strong bases break apart just fine, but the weak acids do not. So HCN stays HCN, even though sodium and hydroxide break apart and sodium can cancel out. One other such reaction that we'll often have that's a driving force is gas forming reactions. Occasionally, some aqueous products will be unstable and will decompose to form a gas. That will also be a driving force. Anytime the gas can leave, it's going to drive this apart. So, carbonic acid will naturally decompose into water and carbon dioxide. That's why your soda will go flat over time, because the CO2 will not always remain dissolved in the water. Sulfurous acid can break down into SO2 gas. And ammonium hydroxide can break apart into water and ammonia gas. So while NH4Cl plus ammonium hydroxide forms sodium chloride and ammonium hydroxide, this shows no change in state. Because the driving force is the production of gas, we actually see a reaction. That we form ammonia gas and water liquid, and that's an actual reaction. That's the actual reaction we end up seeing. So before we go into redox, I want to pull up some examples and once again do some examples of some of these reactions. So if I just did say our strong acids are HCl, HBr, HI, HNO3, H2SO4, and any perchlorate or chlorate acid. Those are our main ones that we have to worry about. Every other acid is considered weak. Our strong bases are all the group 1 bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and a few of the group 2. So barium hydroxide is one of the main ones. Maybe strontium hydroxide. That's depending on the solubility. But then we start to lose the strength. But these are the main ones. If it contains these guys, it's definitely strong. Just about everything else is weak. So if I'm saying HClO4 plus NaOH goes to H2O and NaClO4. I can look this up. I can look up on the table. That's aqueous. There's a liquid. Aqueous are net ionic. First, let's do the total. H plus, ClO4 1 minus, Na plus, OH minus. The key, remember, is water stays together. Na plus and ClO4 minus. Chlorate cancels chlorate. Sodium cancels sodium. H plus and OH minus goes to water. But our weak acids, they're a little bit trickier. Weak acids. So if I did HF and lithium hydroxide, still forms water and a salt. But this guy is aqueous, a liquid, aqueous. But when we write the net, this is a weak acid. Li plus and OH minus. Water and Li plus and F minus. So the only thing that cancels is lithium. Similarly, if I did 2 HCl's and MgOH2, 2 waters, and MgCl2, aqueous, liquid. There's technically a solid and aqueous. That guy is not really soluble. It's not really soluble. So the net ionic becomes 2H plus and Cl minus and MgOH2, because that's a solid, it stays together. 2 water liquids, Mg2 plus and 2Cl minus. The only thing we can really cancel out is the Cl minus. That acids break apart the solid to form 2 waters and magnesium ions dissolved in water. So just keep in mind, we may have situations like that. So redox reactions. That's the last major driving force. A redox reaction involves the change in oxidation states via oxidation and reduction reaction. They must always happen. Must always have an oxidation and a reduction in order for this to go. Because just like heat, as we'll see later, the heat has to form somewhere and has to go somewhere. We have to lose heat. Someone has to gain heat. If I am getting money from someone, someone is spending money. Someone is paying me, and I am getting paid. So electron is lost from one element, and it must be gained by another element. Now, it could be a the same type of element. They could be splitting apart, but they could also be different elements. Now, in oxidation is defined as the loss of electrons, and this results in the increase of the positive charge. So that could be going from negative charge to less negative, negative charge to neutral, or neutral to positive. It doesn't really matter. Or positive to more positive. Going from copper 1 to copper 2 plus is oxidation. But so is going from iron to iron 2 plus. So is going from chlorine 1 minus to chlorine neutral. All these are oxidations. A reduction is just the opposite. A reduction is the gain of electrons. Because you're gaining a negative, you're decreasing the positive charge by increasing the negative charge. The easy mnemonic for this is oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. There's more than just this mnemonic, but this is one that is particularly easy to remember. Oil rig. Oxidation is loss. Now, in terms of this, oftentimes, you will see later, something needs to be doing the oxidation. In most reactions, the thing doing the oxidation is oxygen. Thus the name oxidation. Oxygen, oxidation. So oxygen is causing elements to lose the electrons. But so, in order to figure this out, we needed to be able to determine the oxidation numbers and to figure out whether a redox reaction is occurring. We must figure out if there is a change in oxidation state. That's the easiest way to determine this. The charge of each element, either by itself or in the compound, is known as the oxidation number or oxidation state. Now, here are some rules. If you have trouble remembering any of these rules, write them down on your cheat sheet. By all means, give examples, show this. But for the most part, these are straightforward rules. These are not meant to challenge you. Rule 1, all pure elements, whether this is the element by itself or as a diatomic gas, if it does not have a charge associated with it and it's only one type of element, it is considered 0. So O2, 0. Sodium solid, 0. If it is not charged and it's by itself, it is considered to have 0 charge. It is at its normal valence electron count. All monoatomic ions are thought of to have an oxidation state equal to their charge. So if I see a sodium plus, I'm assuming that sodium plus is charge of 1 plus, that it has an oxidation state of +1. That if it's a Cl1 minus, the oxidation state of the Cl is 1 minus. If you're writing a net ionic equation, we're assuming the charges are what they are supposed to be. Now, please note, while this is not new, we have maybe skipped some steps to get this. But remember, the sum of all the oxidation states in a formula must equal the charge of that formula. So in nitrate, NO3 1 minus, the total amount of charges in NO3 1 minus must add up to be 1 minus. If I have CO2, which is neutral, the total amount of oxidation states in this formula must add up to be 0 because CO2 is neutral. So whatever the oxygen and the carbon are, they have to add up to be 0. Whatever the nitrogen and the oxygen are, they must add up to be -1. So each hydrogen atom in a compound, we will assume it to be +1. There's one key exception, and that is when the hydrogen is bound to a metal. That is so rare, we will almost never see it, at least in what we're going to talk about. Now, there's plenty of other times when it will be -1 with a metal, but we will almost never see it. Not in this class, that is. So if you see a hydrogen in a compound, let's assume it's group 1 +1. Oxygen is group 6. It's almost always going to be 2-. The only exception is in a peroxide, where a diatomic oxygen is 2-. But that is almost so rare as to not be seen. It will almost always have to give a hint that it's a peroxide. So it's not something we're going to always need to be looking out for the most part. All group 1 metals, or alkali metals, will be +1. All group 2 metals in a compound will be +2. Nothing is new here. Nothing is new. Halogens which is group 7, especially fluorine, are almost always -1. The exceptions to this case is in the presence of oxyanions, or where the halogens are the center atom in the Lewis structure. But anytime you have the halogens as a monoatomic, they're almost always -1. Every other element can be determined via context, so we have to think about what it's bound to. But this is kind of how we've done it before. How did we figure out that iron was 2+? We looked at everything else, what's with it to make it 2+. So with that in mind, let's see this. So if I have K3P, I'm going to write these down and we're going to work them out. Some of these are easy, some of these are hard. But you need to be able to figure these out. Some of them are neutral, some of them are charged. Not that making them neutral does, not that them being neutral necessarily makes them easier. But anytime we can figure out is via context, clues, you're on the right track. So, okay, now I wrote them all down and we'll break it down. Okay. We have a rule. Okay, so it's step 1. What do I recognize right away? It is neutral. So the sum of all the potassiums and all the phosphides must add up to 0. Now, potassium is in group 1. Group 1 metals are always +1. Now, there are 3 +1s. And there is 1 phosphorus. Whatever the charge of phosphorus is, they must add up to 0. 3 + 1, this has to be -3. So the phosphorus is -3. Now this one is actually, we can just use our rules. However, show that this works. The total charge is 0. Magnesium is group 2, so it's 2+. What is the charge of hydroxide? Well, if I broke this down, hydroxide is -1, And there's 2 of them. So that means there is 2 oxygens. Each oxygen is group 6, so they're -2. Hydrogen. Each hydrogen is almost always +1. And there's 2 of those as well. So +2 -4 +2 is equal to 0. -2 and +1 is equal to -1, which is the charge there. This one's a little bit more challenging. Okay, there's 2 irons. The net charge is 0. 2 irons. We don't know what the iron is, but there is 3 oxygens. Oxygen is group 6. It's almost always 2-. So, with that being -6, the sum of this must be +6. So iron must be +3. So that's iron 3 plus. Now this one, the total charge must be 1-. Total charge must be 1-. So now we no longer cancel out. So oxygen is almost always 2-. There's 3 oxygens. So there is 1 nitrogen. So if I multiply that together, we have -6 plus whatever nitrogen is must equal -1. So in order for this to work, -6 plus blank equals -1. Nitrogen must be +5. I know nitrogen likes to be -3, but something's got to be positive and something's got to be negative. It's better that oxygen is negative and nitrogen is positive. Please note, I would say oxygen has a -2 oxidation state, not a -6. 3 oxygens together make it a total of -6, but the individual oxygens each have -2. So this one's back to being neutral. We have 1 carbon and 2 oxygens. Each oxygen, we're going to say it's -2. So -4 plus 1 carbon, so carbon has to be +4. So that's pretty straightforward. This guy, there's 1 sulfur and 4 oxygens. Each oxygen we're going to say is -2. The net equality gives us -2. So 4 times 2 is -8. So whatever the sulfur is, sulfur -8 is -2. The only way to get -2 from -8 is by adding +6. +6. So sulfur is equal to +6. Now we have 1 potassium, 1 rhenium, and 4 oxygens. The net effect is 0. We know the oxygens, they are -2. we know the potassium. The potassium is +1. The only thing we are left guessing on is rhenium. So let me move this, rearrange this equation. Rhenium +1 minus 8 is equal to 0. 1 minus 8 is the same as -7. So rhenium minus 7 equals 0. Rhenium must be +7. Okay, we can get that. We have 1 magnesium, 2 chromiums, and 7 oxygens, and all that adds up to 0. We know the magnesium, that's 2+. We do not know the chromiums, we'll leave that there, but we do know the oxygens are almost always -2. So that's, if I say that, rearranging stuff, I get 2 chromiums plus 2 minus 14 equals 0. Rearranging that again, 2 chromiums minus 12 equals 0. If I split that in half, each chromium must be +6, because 6 times 2 minus 12 is equal to 0. So chromium is acting as +6 in this incredibly hard one. Dichromate, chromium is acting as +6. Now the last one is a truly challenging problem. Iron 3, there's 3 irons. And 4 oxygens. That gives us neutral. We know what the oxygen should be. Iron, that's a little bit iffier. So 3 irons minus 8 equals 0. The problem becomes oxidation numbers must always be a whole number. We can't have half of an electron. But 8 is not evenly divisible by 3. So in this particular case, and really only this case, in this very special case of iron, iron is a mixed oxidation state. It is 2 and 3+. There's 3 different irons. There's 1 iron 2+, and 1 iron 3+, and a second iron 3+. And if we add 2 and 3, we get 8. 8 minus 8 is 0. But this is a very weird one. We are mixing 2 species of iron. Iron oxide, iron 2 oxide, and iron 3 oxide. When we put those together, we get the iron Fe3O4. But it is a very special case. I throw that in there as a trick problem. So while we have all these great rules that will help us determine whether a redox reaction has taken place, there is some other ways to make our life a lot easier. Whenever we see a single displacement reaction, it is always a redox reaction. A true single displacement is always a redox. So if I have two aluminum solid and iron oxide, iron 3 oxide goes to iron solid and aluminum oxide, that is a redox. I do not need to calculate the charges to know that is a redox. Why? Because there is a pure solid. One of the hard, fast, easy rules is whenever you have a pure element being incorporated into a reaction, it is always a redox because the element is always zero. And if you're becoming something that is not zero, you are changing your oxidation state. So it doesn't matter whether iron is going from 3 plus to 0 or 2 plus to 0, it is dropping. It doesn't matter if aluminum is being oxidized or reduced, it is going from 0 to not 0, so a reaction is taking place. Now, many combination and decomposition reactions are also redox, but unless there is a pure element being formed or consumed, you must check the charges. Check the charges, the oxidation states. Now, because of the nature of the push-pull of a redox reaction, one element is always oxidized, causing a reduction somewhere else. So the terminology gets a little tricky. But we often call the guy who gets oxidized a reducing agent because it's often doing reduction on something else. The same is true for the element who's getting reduced. It's the oxidizing agent because oftentimes we don't care about one of those. We only throw the oxidizing agent in to oxidize something. You go, I want to oxidize this compound, so I throw in an oxidizing agent. Sure, that guy gets reduced, but the oxidizing agent does its job. But anything that is reduced is the oxidizing agent. Everything that's oxidized is the reducing agent. But in this equation, so aluminum and chlorine, aluminum goes from 0 to 3 plus, and so it's being oxidized. Thus it is the reducing agent. Chlorine is going from chlorine neutral, 0, to chlorine 1 minus, so chlorine is the oxidizing agent because it's getting reduced. So all these are examples of oxidation reduction reactions. I'm going to skip the first one and look at the other guys first. The other guys are clear redox reactions. I do not need to even consider the charges, but I will. O2 is a pure element. Consuming O2 to go from carbon monoxide to carbon dioxide means oxidation must occur. So carbon is 2 plus on the reactant side and it's 4 plus on the product side. So oxygen is being reduced from 0 to 2 minus, but not all of the oxygen. Only the O2 oxygen is being reduced. The other oxygen is staying 2 minus. And the carbon is being oxidized. Here's our rare peroxide. H2O2 is being oxidized and reduced to form water and oxygen. It's a decomposition reaction. Now you're like, okay, well, what guy's being oxidized? What guy's being reduced? Well, let's look. H is typically +1, except when it's bound with a metal. So H is +1 on the left, H is +1 on the right. O is -2 in water, but is 0 in oxygen. And if this is peroxide there, peroxide is the oxygen is considered 1 minus. So in this very rare well, it's not very rare, but in this instance, oxygen is both being oxidized and being reduced. One peroxide is going up, one peroxide is going down by an electron. And then, of course, aluminum and iron 3 oxide going to iron and aluminum oxide. Now, how would I tell the top reaction? Well, I'm going to have to look at all the charges. It doesn't matter if you can figure out one of the charges changes, there must be another charge change. We could do it this way that we just did dichromate in the last problem. Dichromate being chromium 6. 2 chromium 6s are going to 2 chromium 3s. That is a clear example of reduction. Or you could go iron 2 plus. That's iron 2, FeO. 2 plus cancels with 2 minus. And then we have iron 3 right there. Iron 3, Fe2O3 is iron 3 plus. So 2 plus goes to 3 plus. Either one would tell you this is an example of an oxidation reduction reaction. And the last slide for this chapter is all about activity series. The idea that if we have a chart like this, we can predict reactivity, because not all reactions, oxidation reactions, will occur. So I just want to think about this real quick. I want you to think about this. Go back to my dockhand. If we have do our aluminum plus iron 2 oxide goes to aluminum oxide and iron. We said that reaction occurs. It's a redox reaction. Well, would the reverse reaction occur? Would the reverse reaction occur of 2 iron plus aluminum oxide splits back into iron oxide and 2 aluminum? And the answer is no. Because essentially we're here is our, I'm going to call that the reactant, and that's our product. We actually kind of have we're here on the R, and we have our P. So the reactant's naturally going to fall from a high energy state to a lower energy state. And it's going to get stuck there. So the likelihood of us climbing back up the hill, no, there's no driving force. The driving force going down is essentially gravity pulling this rock down into the well. But to move that back up there, you're going to have to put in a bunch of work. You're going to have to roll that rock up the hill. It's not going to spontaneously roll back up the hill on its own. So not all redox reactions will happen, even though you could write one. So with that in mind, come to our activity series. That, as I said, all single displacement reactions are redox in nature. That we can look at that calcium plus water forms calcium hydroxide and hydrogen gas. Cobalt will not react with water, but cobalt will react with HCl, which is in strong acid, to form cobalt chloride, hydrogen gas. These reactions are an example of corrosion. Now, not all single displacement reactions will occur. They are categorized into activity series. And the basic idea that any metal that is higher on this table is more reactive towards oxidation than metals lower on the table. So any metal that is higher up on the table will replace any metal that is lower on the table by single displacement. So if we look here, iron is right here, copper is down here. So iron will react to replace copper. So if I mix copper oxide with iron, iron replaces copper. But if I try to do the reverse reaction, copper replaces iron, the answer is no, it will not go. So if you're given a chart like this, you can predict reactivity based on where things are. So, for example, these guys are highly reactive. Cold water. So water without energy added into it will spontaneously react to give H2. Now, these guys will not react with cold water, but if you shoot steam at them, they're reactive enough to produce hydrogen gas. These guys won't react with water at all, but in the presence of strong enough acid, they will form hydrogen gas. And the last set, notice it's hydrogen. There's hydrogen where the defining line. This last set do not react at all to give hydrogen gas. They will not be able to replace hydrogen because they are below hydrogen. So notice copper, silver, mercury, platinum, gold. A lot of these guys are coinage metals, are rare metals. They do not react. It's good. We are not going to accidentally, whoops, I dissolved my gold. It is not easy to dissolve gold. You're not going to lose your gold. You're not going to lose your silver. It's not easy to do. So a simple reaction, I'm going to light up a reaction, and we're going to look at it real quick and be able to predict, well, will this reaction occur? Okay, predicting whether these guys will occur. So, real quick, this is our last slide. So, magnesium and zinc. Will magnesium replace zinc oxide to form magnesium oxide and solid zinc? And then, will lead replace zinc to form lead oxide and zinc, solid zinc? So remember, magnesium, lead, and zinc. Magnesium, lead, and zinc. So looking at here, we see magnesium right here at the top of the green. Zinc is about in the middle of the green. So will magnesium replace zinc? The answer is yes. But lead here is the bottom of the light blue. Will lead replace zinc, which is the middle of the green? The answer is no. So no reaction will occur. So that's a big no. Now, please note one last thing here. I just want to point this out. Note zinc and iron. They're pretty close together, but zinc is above iron. Iron is our steel, our products that we're going to use to build buildings with, and we want to stay around for a period of time. So one way to protect it is we coat it with a more reactive metal. That will be a sacrificial anode. You'll learn more about this next semester if you have to do it, but galvanized steel is steel that has been coated with a thin layer of zinc. The idea, if the iron ever were to start to rust, the zinc would then replace it with the zinc oxide and reconvert the iron back into neutral iron, and thus keep its strength. So that is basically what galvanized steel does. But that is the end of this chapter. When I get back, we will start some review for the test. Have a good day.